Let's go through a couple of examples with change in slope, either going from a steep slope or a mild slope to the opposite, and a step down at the same time. So we'll get two different normal conditions, and we'll get to do some energy balance stuff, and we might get to do a hydraulic jump. So here's our first example. If we, the first step is to get normal and critical depth, and so we've got a section A and a section B. We're going to get normal depth on both of those. So let's set up table, and we're looking for normal depth at A, and we might not need it, but we'll write down the energy, the Froude number, and then also at critical. So I've plugged all the information in for section A. Bottom width, we don't know the depth yet. We're going to figure that out. The side width, this is a 3-to-1 slope. So this is, a walkable slope. And then we've got like a clean, smooth concrete finish. And so we need to set this normal depth flow rate equal to 5,500, and that'll tell us the depth that corresponds with uniform conditions. So if this channel was super long, either upstream or downstream, and we didn't have any downstream impacts to this section, then this is what the depth the water would be flowing at. So 5.99, and our energy is 7.68. And the Froude number was less than 1. I didn't write that one down, but we'll get it. So 0.842. Let's get the downstream normal depth. So this is section B. I just changed the bottom slope. So we got 3.09 and 10.91. And then we need to get critical depth. So we're going to goal seek the Froude number to be equal to 1. And that's 5.32. So we can sketch this out. We've got critical depth, and we've got normal depth, and then we've got this change in slope. So it's going to go from subcritical depth upstream to a supercritical depth downstream. And there's also this step here that's happening. And so that step height is 4 feet. So it's going to kind of boost the water as it goes downstream. So what we need to do is we need to separate, define some sections, and then we need to try and figure out what we do know. So if this is right at the crest, we'll call that section 1. And this is right below the crest. That's section 2. What do we know? Well, we know that it's going to go through critical. Anytime we go from subcritical to supercritical, what happens is the water accelerates, and it happens to go over critical right at the crest, and that has to do with the fact that critical depth corresponds with the minimum specific energy that's needed to pass the flow. So if we plot out that specific energy diagram, this point right here, the minimum energy, that's critical. And that kind of makes sense intuitively that this point where the break happens controls what's going on upstream. If we wanted to lower the depth upstream, we would need to move that change in slope farther upstream. So now we know that point, and we also know that this is going to be an M2 curve. And so then the question is, what happens downstream? And it's going to go supercritical, so it's just a question of, does the final depth land above normal depth or below normal depth? And so that would either mean an S2 curve or an S3 curve. So what we need to do is we need to find out what is Y2. And so to do that, we're going to use our energy balance approach. And so what we're going to do is we're going to say that the energy at 2 is equal to the energy at 1 plus the energy that it's gaining as it goes down that step, 4 feet. And so the energy at 1, that's critical energy. If we put in the numbers, we get and then we do a goal seek. So actually we now know, so if we go over 4 feet, that gives us 11.57. So what we want to know is, what is this depth? Y2. So we're going to goal seek that. Oops. So what we need to do is we need to make sure, because we're looking for a supercritical depth, we need to make sure that our first guess for Excel is supercritical. So I'm just going to put in a low value, make sure our fruit number is greater than 1. And then we're going to goal seek, we're going to set that energy to 11.57 by changing the depth, and Excel's going to do the guessing. We got 2.96. So goal seek tells us that Y2 is 2.96 feet, which is less than the normal depth for section B. So now we can plot this out. What happens is we get a local change through this acceleration section, and then a corresponding S3 curve. So that's the water surface profile for that one. So it's not super exciting, but it is an opportunity to take a look at water surface profiles and change in slope and a change in energy. So the next example is the same slopes, but we've just switched places. So you can see that I've got section B upstream now and section A is downstream. There's still a down step of 4 feet. I've went ahead and copied the info from the previous problem right here. We've already done that. So we know what normal depth is. We know what critical depth is. So let's sketch out what the kind of the control points are. So here's critical depth. Let's get normal depth in there. And so we see that there's a conflict of controls. So the downstream section is controlled by downstream conditions, and the upstream section is controlled by upstream conditions, and those two are going to come together, and there's going to have to be a hydraulic jump. So the question is, where's the hydraulic jump at? Is it a complete jump? The jump could happen right along this, this step down, or it could happen upstream of the step down, or it could happen downstream of the step down. So we've got to go through and just try and analyze what the momentums are at those specific places. So we've got to add a column or a location for momentum at each of these depths. So we're just going to go to the spreadsheet and we'll type in our number, 3.09. That is the normal depth for the downstream condition. Sorry, the upstream, the steep slope. So we've got our specific force, the momentum of 4199. We'll write that down here in a second. And then we want to type in our upstream, sorry, that's the downstream slope. So that's 3253. So right away, it sort of indicates that there's more specific force in this section than there is in this section, which indicates also that if there was no step down, that that the hydraulic jump would be downstream of the change in slope. So if there was no step down, there would be hydraulic jump downstream. In fact, it's probably a good idea to draw this out in a specific force diagram. So that's YB, the upstream depth, and then we get YA, that's the downstream, the YA, that's the downstream depth, and that specific force is less than. So if there was no downstep, the jump would be downstream because the momentum at section B is greater than the momentum at section A. Now, additionally, what that means is that if there is a downstep, we're going to increase energy. So if we take a look at the energy diagram, we're going to move from section B, we're going to gain energy as we go down the step, so that the water depth is going to become even more shallow. And that means we'll have even more specific force. So we'll, with the 4-foot step, we'll move from this point down to another point. So that makes it even more likely that the jump will be downstream of the change in slope. So let's do that. We'll operate under the assumption that the jump is downstream. So what we need to do is demarcate some points of interest. So we've got section 1 and section 2, and we want to know what's going on at section 2. So we can actually sketch this in now. The water surface profile will be uniform. It's under upstream controls, and so it's going to stay at uniform conditions until it runs into something that changes it. So that's uniform conditions, starting upstream and going downstream. And then it's going to accelerate as it goes down. So it's going to get shallower. It's going to gain energy. So the energy at section 2 is the energy at section 1, which is normal energy for section B. Plus the 4 feet of step. So that gives us 14.91 feet of energy. So if we wanted to, we could actually mark this out as 14.91. This is 10.91. This is the normal depth for section B. And this change is the change in elevation, delta Z. So now we know what the energy at section 2 is. That's going to give us the depth at section 2. We're going to goal seek that. So this is going to be a supercritical answer. We want to make sure our first guess is supercritical. I'm going to put in a small number, and then we're going to goal seek the energy. So we got 2.51, and we're also going to write down this momentum. And because there's going to be a downstream hydraulic jump, we're going to do the delta X calculation. I'm going to go ahead and copy that information right here. This is the upstream part of the info, so we'll put that in. And so we'll take note of the specific force and the hydraulic radius and the velocity. So we're going to write those down also. And then, so we can sketch this part out too. Downstream controls in the subcritical section, and it's uniform conditions all the way up to the hydraulic jump. So what we end up with is an M3 curve to a hydraulic jump, and then it's uniform conditions from there on out. So our delta X calculation is going to take place from this point to this point. And so we need to know what's going on here at this section. Let's call that section J. And here's delta X. So in order for us to get section J, or to get delta X, we need to know what's going on at J. That's going to be a specific force problem. We will do the force balance. It will find the conjugate depths of normal depth. And so if we look at that, here is the normal depth for section A. That's this side of the jump. And then we want the conjugate depth of that. That's this side of the jump. So what we want, so this would be, that's YJ. And we're going to use goal seek to do that. We're going to goal seek the momentum this time. And this is a supercritical answer. And so we've already got a supercritical number. That's fine. So we'll goal seek specific force. We're going to set that to 3.5. Oops. By changing the depth. And so we got 4.7. And then we're also going to take note of the velocity and of the hydraulic radius. And I'm going to copy these cells into this portion. Now the delta X calculation is wrong because I need to change this slope to match the slope where the delta X is happening. And so that is 0.001. All right, so here's our delta X calculation. And there's some rounding difference, so we'll get basically the same answer, slightly off. Let's write all that information down. So the momentum, oops. The momentum at section 3 is equal to the momentum at section J, which is 32.53. And that's going to give us the depth at section J. I said that was section 3, but let's call that was the normal depth for section A. Let's fix that. So we need to know for the hydraulic radius at section 2, at section J, and then the average, and the velocity. So we'll use those two average values for our delta x calculation. So we need SF bar. And we want to do the smell test on this one. So the slope of friction should be less than the upstream slope, but greater than the downstream slope, because we know that the water's slowing down. In fact, there might be a case if this step was big enough that the slope of friction in this section would actually be greater than the upstream slope, but it would be a point of reference. So the delta x calculation is moving from section 2 to section J. So we put in the energy for section J. And then that's subtracted from the energy at section 2 over the bottom slope. And so that was 1125 if we do the calculations by hand. So, you know, this is another hydraulic jump energy. This is a kind of problem I put on a test. So if you wanted to practice for the test, maybe go back and try to work this problem without any of the answers. Or you could go back in and change the flow rate slightly, and it should give you a similar kind of a solution. So it's nice that we know kind of what's going to happen here. On a test, you're not going to know what the shape of the water surface profile looks like. This thing is going to be a little bit different on the test, and you'll have to try and decide. So it's good to practice this in a vacuum where you're not looking at the way that I'm working the problem.